introduce a new faculty member. So please join me in welcoming to UC Berkeley Nuclear Engineering, Professor Ellie Tubman. And given the number of people, I'm assuming that everybody's excited about fusion. Yeah. So, Professor Tubman joined us from Imperial College. She graduated with a Master in Physics from the University of Sussex in the UK. Then she got a PhD from the University of York. And after that, she had 2 postdoctoral positions. First at the MagLIF Power Group at Imperial College, and then at the Lawrence Livermore National Laboratory on the National Ignition Facility. In 2023, Ellie took up the position at Imperial College London as a lecturer in experimental high energy density plasma physics before joining UC Berkeley in August 2023. And we'll know now everything about what she's doing in fusion. So again, welcome.
So it's so lovely to see so many of you here today. Thank you for coming along, and thank you for the invitation to give the first colloquia of this semester. So I'm very excited to be here. I literally arrived in the States 3 weeks ago, so I'm still very new to being at UC Berkeley here. But yeah, today I figured that as I am new to the department, I'd like to introduce you to a few of the different areas that I research. So some of them are covering fusion energy, some are covering diagnostics, some are actually investigating astrophysical plasmas. So I've given my talk title here, Here Comes the Sun, who for anyone who's a music fan, you might recognise these as being the British band The Beatles, so hopefully I can put that song in your head and get your week started off to a good start. But yeah, so we're going to talk about some approaches to fusion energy. And as I say, this is going to be sort of a broader overview of some of the different areas, so if anyone wants to collaborate or work with me on some of these projects, please do feel free to come and chat with me at any time or drop me an email. I'm very happy to discuss what I'm getting up to, and I will need extra help on several of these things as well. So yeah, Max already introduced myself a little bit, but where did I come from? So you can see myself down in the bottom left-hand corner there. That's me in the centre as a 14-year-old doing science, and I always loved science for the amount of questions that you could go in and ask and try and figure things out. Although actually at certain points in my life I've wanted to be a dancer, an events manager, so there's been a whole breadth of things that I've been interested in. But I did do my undergraduate in physics at the University of Sussex over in the UK, before then doing my PhD working on magnetic field generation and laser plasma interactions. I then worked on MagPi, which is at Imperial College down in their basement, which is a pulse power machine. So some of my research now is actually still involving pulse power. I then was a postdoc on the NIF, the National Ignition Facility down the road. I started that position in March of 2020, so really good time to be joining a new job. But I was the backscatter responsible scientist, so I was analysing the data for light that gets reflected back down the laser chain, because if that happens in large quantities you can end up damaging your optics, and that's something that we really need to be watching out for. So I was analysing each of the experiments to check we weren't getting too much backscattered light. I was then involved in other experiments which I'll be discussing again still today. I briefly moved back to Imperial College in London, but then, yeah, 3 weeks ago, turned up here again. So in my free time, I enjoy sailing. So this was in Florida earlier this year. I sail J24, so I actually dance about on the front of the bow, so still maybe that dancing career I was after. But yeah, I also enjoy backpacking, cycling, triathlons, and this is my family member down in the bottom left-hand corner here. This is Zeely. So yeah, so that's a bit about me. Another really important part of research, I feel, are the collaborations. So these are some of the institutions and people that I've collaborated with, and I hope to only be adding to this list as I go through my research. Yeah, so what am I going to talk to you about today? So I'm going to introduce several of the fusion approaches that are out there, for those of you that aren't as familiar with fusion. I'll then jump into discussing Hohlraum physics, which is the approach taken at the National Ignition Facility. the focus that I have is actually looking at the magnetic fields that get generated within these fusion plasmas, how we're also able to diagnose these fields using protons, and then also going to discuss MagLIF, which is magnetized liner inertial fusion. So a combination of pulse power and laser driving that fusion approach, and we're actually doing some of these experiments over on the neck as well. So I'll talk to you about some of this laser heating of gas pipes, as well as then how we are trying to measure raw material that gets mixed into the gas to our fuel as well. So firstly, when we're going to talk about fusion, we're going to be discussing plasmas. So for those of you that don't know, plasmas are a hot ionized gas. So you've essentially separated out your ions and your electrons, which means that when you apply magnetic or electric fields, you're going to start having these particles moving about and responding. You're able to set up waves within your plasma. And these plasmas are found in many, many different situations throughout the universe. But the thing is that astrophysical plasmas, if you're trying to actually study them, you've got to send up probes, you've got to send up satellites to try and actually understand what's going on. So that's pretty difficult. A lot of the time they're really, really far away. Sometimes when we're measuring signals, maybe we're using another star to give us a backlighter to image something else, and we're then trying to understand the signals and the absorption that might have happened along, for example, that light that's travelled through that other object. That's a lot of complexity to try and unpick when you're actually making these measurements. You've also got really low particle densities in some of these astrophysical plasmas as well. So it's very hard to collect enough statistics to really understand what's going on. But we can do some of these experiments in laboratories. So some of the things we can go out and study are things like radiative reverse shocks. When you've got two stars in close proximity, one is going to be accreting matter from the other. And as that matter comes in and approaches the, actually, I'm on the wrong side here. As that matter comes in and reaches the atmosphere of that second star, you can end up forming shock waves there where those densities, those two materials are meeting one another. And we can study those within the laboratory. Obviously, we can also do fusion that happens within stars. We can also see how magnetic fields applied to these plasmas affect the transport of energy within these environments. We can do experiments on magnetic reconnection. So that's the process by which, when you have magnetic fields coming together, opposing one another in direction, that's an unstable configuration. So the field lines break and they will reconnect. But in doing so, they release energy. And this is actually the process via which the Northern Lights gets formed. And this was actually the topic in part of my thesis research. We can also do studies on the equation of state of planetary interiors. And another area that I am still doing research into is the production of collisionless shocks and particle acceleration. So what kind of facilities can we actually do these experiments on? Well, there's experiments worldwide, and this is a map of just some of the facilities that are out there. There are plenty more, but you've got laser facilities that are listed here. We've got accelerators that are given by the dark blue stars on these maps. And then we've also got some pulse power machines given by the green stars. Now, I've got some photos here of some of these facilities as well. So at Sandia National Laboratory, we've got a pulse power machine called Z. This one is actually called Z. When I refer to pulse power, sometimes I end up saying Z. But this is the Z facility. And this is a pretty cool image here, because what you have is your target would be loaded in the center here, and surrounding the target are capacitor banks. And that is where you store all of your energy, your charge, until you're ready to discharge all those currents. And the currents then are meant to run through pulse-forming lines to your target, which they then run through and create you plasmas. What you don't want to happen is all of those currents to actually find their own way to the ground without going through the pulse-forming lines. And so what we have happening in this photo here are all these little lightning bolts where the charges are doing exactly what we don't want them to be doing and finding their own way to ground that's not through the pulse-forming lines. So it's a really cool photo, but it's not great for the experiment. So other facilities that we have, the National Ignition Facility, a laser facility down the road from here that I'm sure lots of you have heard of. There's also the Orion laser over at AWE, which I've done several experiments, and I've got experiments coming up on as well. And you can see here, these are some of the amplifier chains to create the lasers. This is a very similar laser set up to the Omega laser that's over at the University of Rochester. And then we also have particle accelerators, such as DAISY over in Germany. And when you look from an aerial view, you don't see much of the accelerator, it's mostly all below ground. And then you'll have your experimental facilities dotted about here as well, where you can bring those accelerated beamlines in and do whatever physics experiments you're wanting to do. So those are some of the facilities that we have. So one of the experiments I'm obviously very keen on, and I'm sure lots of you want to hear more about, is fusion. So we often do fusion using deuterium and tritium, so hydrogen isotopes. And the reason that we do this is because at the energies that we're driving our fusion implosions with, we want the highest probability that that interaction is going to happen, that that fusion reaction is going to happen. So when we bring our tritium and our deuterium atoms together, we have to overcome the Coulomb potential, which is trying to force them apart. So we have to provide them energy to overcome that, and then hopefully they provide us with a neutron carrying 14.1 MeV of energy and a helium particle, alpha particle, that comes out as well. Now, that neutron, if we were looking to do fusion energy as a power plant, you might then surround your reactor with a water blanket, so your neutron will go through, heat up that water, dry your steam turbines to then produce you commercial electricity. Maybe a little bit simplified, but that's the idea of it. The other thing that gets talked about a lot with fusion is the gain, or the Q factor. And this is the amount of fusion power out divided by the energy in. So when you start getting to gain of greater than 1, you've started to produce more fusion power out than the energy that you put in. And this starts to become, so you might have put in a lot of energy, but you've got to make sure that you've got enough fusion interactions happening in your fuel to actually produce more energy out than you've put in the first place. When you get ignition, or when we talk about ignition, we've got a gain of greater than 1. Now, there is the Lawson criteria, which actually indicates the density and the confinement time to achieve ignition. So if you have densities given by N and confinement times here, TE, greater than 10 to the 20, then you've met the Lawson criteria. And this is basically talking about the probabilities that you've got enough fusion reactions happening. So the higher your density, the more particles there are, the more fusion reactions hopefully you will have taking place. And the longer you've confined your plasma and driven it for, the more probability again that you've got fusion reactions that will be taking place in that time. So when we look at different approaches, we've got magnetic confinement fusion over on the left here, which is the approach where they confine their plasmas using magnetic fields. It's the approach adopted by tokamaks, stellarators. They have densities of about 10 to the 14 cubic centimeters. Their confinement times are of the order of seconds, and they use 100 kilogauss magnetic fields to confine their plasma. Their volumes at the moment are of about 8 times 10 to the 8 cubic centimeters. They're increasing their tokamaks as they're building ITER, and demo is that will be a later stage reactor as well. When we go to magneto-inertial confinement fusion, this is discussing the approaches such as MagLIF, using pulse power, so also then Z pinches. And these are densities of 10 to the 20 cubic centimeters. We're getting to slightly shorter confinement times now of the order of microseconds. We can produce magnetic fields in these experiments, but we also can apply magnetic fields of up to 50 to 100 megagauss. And the volumes have decreased now to 8 times 10 to the minus 5. When we go to inertial confinement fusion, 2 of the key approaches taken here are direct drive and indirect drive. So direct drive is when you actually are heating your fuel directly with your lasers. Indirect drive is when you are heating a Hohlraum, which I'll explain on the next slide, to actually then produce your X-rays to indirectly drive your fuel. We get densities of about 10 to the 25, time scales are on the order of nanoseconds, and again very small volumes, 10 to the minus 8 cubic centimeters. So there are lots and lots of different fusion companies that have been popping up over the past few years. These are just some of them listed on this slide here. but they're all adopting slightly different approaches and maybe combining some of these different methods to actually achieve fusion. These are just some of the ones that are out there. There are also ones that are looking at more of the technology side, so whether they're developing the optics that might be needed, or the laser technology, or the diagnostic side of thing. There's a vast array of different research being done out there. So let's have a look at inertial confinement fusion then. So, as I say, this is the approach being done over at the National Ignition Facility. What you have are these Hohlraums, which are these gold cylinders, where you bring in your lasers from the top and the bottom through what are called laser entrance holes. You hit your laser onto the side of the Hohlraum, the gold wall. This then creates you a plasma. It gets really hot, it emits X-rays. The X-rays then come out, heat your fuel capsule that's in the middle of those Hohlraums, and then you ablate off the outer layer, which drives a rocket-like effect to push and compress your deuterium-tritium fuel in the centre here to hopefully then give you ignition. And you can see a photo of a Hohlraum down on the bottom of this slide here. They're pretty small targets, sort of 10 millimetres in length, and you can see the little apertures, the openings at the ends there for the laser entrance holes. Now, when you have your lasers coming in, if you had a vacuum Hohlraum, your lasers would cause you to have a gold bubble, a gold plasma that it would expand out off the wall of the target. This then could come out and end up impacting on your fuel that's in the middle there as well. Anyway, you've got this plasma that's expanding out off the wall. It could impact that central fuel. And so what they ended up doing was putting a gas inside of the Hohlraum to kind of add a bit of pressure to push back on that plasma from expanding so far. Because you've also got the fuel that's in the middle there that is also going to be expanding outwards, and you don't want the two, the gold and that ablator, that fuel capsule, to be interacting with one another. Now, there's a lot of other effects that start happening in the Hohlraums as well when you've added a gas. So your lasers, as you're propagating through that gas, is also going to be creating a bit of a plasma as it travels through the gas itself. You've got a laser, which is basically a wave, electromagnetic wave going through a plasma, and the plasma we've already mentioned can also support waves. And you end up having an interaction between your laser and your plasma that can end up generating lots of instabilities. One of these instabilities was looking at the backscattered light that I was doing as a scientist on the NIF. So looking for any light that's being reflected back off these waves in the plasma back out of the Hohlraum. So we're now not getting our lasers that are heating the wall anymore, they're being absorbed in the plasma, in the gas as they're going through. We started working on this and tailoring the gas fill density on the NIF to try and then mitigate for some of these instabilities, some of this backscattered light, so we weren't losing as much to that effect. The other thing that we found was happening was something called cross-beam energy transfer, CBET, which is essentially when you've got these lasers coming into your Hohlraum, you've got regions here where your beams are crossing one another. So they're going through regions of plasma, but the laser beams are also crossing one another. And when they do this, they can end up generating beat waves that transfer energy from one of the beams into the other beam. So the lasers start talking to one another and transferring energy over. That say, for example, you wanted to have a uniform spread of all of your energies across that wall of that Hohlraum. If these laser beams are now transferring energy from one to the other, you might now end up with more energy being deposited at the centre of the Hohlraum and not down at the ends. So now we're going to create more X-rays from here rather than from down at the ends. But then when it comes to ablate our capsule, we're going to have asymmetrical ablation going on. And that's not ideal because it's like a balloon. If you squeeze a balloon from just two sides, the balloon's just going to squirt out at either end. That's what's going to happen here. We're not going to be driving the compression uniformly anymore to give us the optimum fusion compression. We're going to have things spilling out in all different directions, which is not great. So we've worked with CBET for quite a while now. There's been some fantastic work going on in this, and this was one of the big things that helped us with the recent ignition shot. But one thing that hasn't really been considered much in Hohlraums is actually the effect of magnetic fields. So I'm going to take a step back for a minute and just explain how these magnetic fields get created. So when you can self-generate magnetic fields when you have regions of non-parallel density and temperature gradients. So I've got a schematic here of a foil and a laser, just a single laser coming onto a foil. When you consider the edges of that laser spot, you're going to have regions of temperature gradients out at the edges. It's going to get cooler as you go further out of that laser spot. You've also got a density gradient that's increasing as you go into your foil. Your foil is a solid material there. You've got a density gradient that's coming off it. And when you have this, when you have these non-parallel density and temperature gradients, we have the Biermann battery mechanism, which can create you these magnetic fields. So now we have a magnetic field that is going toroidally around that laser spot. And we can do experiments to try and measure these fields. And one way of actually measuring the fields in an experiment is by using proton radiography. So protons are a charged particle. When you put a charged particle through an electric or magnetic field, they experience the Lorentz force. The Lorentz force is given up at the top of this slide here. And when those protons are travelling through those fields, they'll experience that force and get deflected. So they'll be deflected off where they should have fallen originally. We can analyse what our detector images end up seeing and work out where those deflections have come from. And then we can back it out to going back to our plasma to work out what the electric and the magnetic fields were to form us that deflection. And there's a set of equations here that we can use to actually work out from the deflection what the actual fields look like at the plasma itself. And there's a very nice paper here by Derek Schaefer et al. That I'd point you to if you would like some more information on proton radiography in particular. Now, we can use those protons to go through our experiments. So these are some experimental data onto what's called radiochromic film. So it's just film that's measuring when a proton hits it, it goes dark. And so here we have a side-on projection, we've got a foil, we've got our laser that would be coming up and hitting that foil, so in the same projection as what's shown in the top left. And you end up with sort of some little filament-like features coming off. We've also got our plasma expanding off the foil there as well, that's a little bit denser, so we're not able to necessarily probe through as easily. We also have a face-on projection. I'm really sorry, this hasn't come out quite as clearly. But you can kind of see there's a circular region in the middle there. That's where our laser spot will be hitting the foil. It's creating magnetic fields around it. And what you can also maybe start to see is there's some other like structures that are coming out, sort of spoke-like filaments around this. And these are not actually fully understood, it turns out. So part of my research is doing experiments to try and understand the mechanism via which these filaments are being formed, and whether they could indeed actually be affecting things that we're seeing in Hohlraums. So this is a simulation of a Hohlraum. So this was run by Jerry Chittenden at Imperial College using the Gorgon code. But if you look over on the right-hand side of the simulation here, these top and bottom regions would be from the laser entrance holes. Where you've got this darker red region, that's where magnetic fields are forming. So we've got fields potentially at these laser entrance holes. We've also got then the bubbles would be blowing off in these regions here. The central region is where the fuel would be. We're not getting fields within that. But we are getting some fields potentially as that gold plasma is blowing out into the background, into the gas fill of the Hohlraum. And I've done some preliminary experiments very recently where actually we think we might be seeing even stronger fields than the simulations are predicting, as well as then some very weird non-uniform fields being driven out there. And so the question that I'm posing for my research is, do we actually understand the fields that are being created in a Hohlraum? Should we care about them? At the moment, a lot of the simulations for Hohlraums and for the fusion experiments on the NIF don't really include magnetic fields that much because we've thought that they're not going to be affecting the physics that much. But actually, it could be that they might need to be included, which will be a bit of a headache potentially for people in simulations because they're not easy to just include. It's going to extend the time that those simulations need to run. But we need to do the experiments to check, okay, are these fields what we think they might be? Are they going to affect our plasma? The plasma transport, are they going to affect where the laser is actually depositing its energy in these Hohlraums? And so that's one of the things that I'm setting out to investigate, and I'm doing some experiments coming up on. So there have been some experiments already done on trying to probe the fields within Hohlraums. So these were some experiments done by Lee et al. From MIT, and you can see here, there we go. So you can see here some proton radiographs of going through an end-on to the Hohlraum. So it's going through the whole length of a Hohlraum. You've got lots of laser spots and things around here. And you can see from looking at these radiographs, they're pretty complicated. There's a lot of structure in them. And you've got to remember that protons are subjected to deflections from electric and magnetic fields. So how are we going to try and pick these apart? And there are some tricks you can start to apply to work out what's electric, what's magnetic, but there's a lot of complexity in these. So some of my experiments are simplifying down some of these experiments just to remove some of the complexity and then build up from there. The other thing as well is that these experiments were done onto a CR39 detector. So over on omega 60 where these experiments were done, typically when you produce protons you use dihelium-3 capsules, which produce you two proton energies, a 3.6 MeV proton and a 14.7 MeV proton. And they then get imaged onto CR39, which is a plastic detector. Now the thing with this plastic detector is you then have to go away and chemically etch it, as well as then scanning it with a microscope to actually reveal your data. And this can take an awfully long time to etch. You can get data maybe sort of a week, if not months later, depending how much data you've got on a shot day. Some shots you might get 14 shots in a day. That's a lot of CR39 to be processing. So one thing that I've been looking at is designing a different way of detecting some of these protons. And I mentioned this, I think, earlier this year, if you saw my talk then. But essentially, we've designed these stacks which include imaging plates. So imaging plates are sensitive to protons. They are also sensitive to electrons, X-rays, neutrons, and so we need to try and work out how to subtract that as a background signal. So this is the detector stack that I've been using. So we have a thick bit of tantalum at the front to try and range down the X-ray fluence that might be falling onto our imaging plate, as well as then it ends up removing the 3 MeV protons and ranges down those 14.7 MeVs so that they deposit their Bragg peak in the imaging plates. Now, we have the first bit of imaging plate to capture that proton signal. The protons also fall onto the CR39 as well, so we can benchmark the imaging plate and the CR39 together. We then have a second bit of imaging plate which is used to capture just the background signal. All the protons are stopped by the time that they reach the back of the CR39. So this then acts as a background signal that we can use simulations to work out how much some of these background signals, like the neutrons, X-rays, how much they would have been attenuated between the second and the first image plate, to then actually see what our proton data looks like. But one of the tasks here is actually going to be running those simulations, and so being able to determine what that background source is and contribution on that second bit of image plate. And just very briefly, if some of you saw the talk from earlier this year, I was discussing these magnetized collisionless shocks. So these shocks are formed in scenarios such as when the solar wind interacts with the Earth's magnetopause. You end up forming a shock wave where your magnetic fields are perpendicular to the flow of the material to your shock trajectory, as it were. And these shocks can end up accelerating particles from those magnetic fields that pile up at your shock front. And we've been doing some experiments to try and observe this particle acceleration, but we've also been using our proton probe to then go through and image the shocks and the fields that get produced in them using these imaging plates. So our experiment is shown in the centre here, where we have a background gas, a hydrogen gas, that we drive a shock from a carbon foil, so that shock propagates outwards. You've got a magnetic field that's perpendicular to that shock propagation. It piles up in front, and we're hoping to see that some of the energy from this carbon shock that propagates out gets transmitted into this hydrogen background gas, and we can see ions being accelerated ahead of the shock. And these are these little targets that we shoot over on Omega. But anyway, the thing that I wanted to show you from this experiment is the data that we collected from the imaging plates versus from the CR39. So we had that detector stack where we fielded both, and you can see here, this is our shock, that's the dark region, this dark curve out in front. That's where the shock edge has propagated out to. The shock has propagated from the top left down to the bottom right. And when we look to the CR39, you can see very similar features to the image plate, which tells us this, yes, it is protons we're predominantly measuring on that imaging plate. We've also then got a second bit of imaging plate for the background signals, and yes, that's also seeing a background signal, it's not seeing structure on there. And we can take line outs across them and see also that yes, the line outs across both the image plate as well as the CR39. And there's a paper I published here if anyone wants more information on some of the imaging plate experiments that we've been doing. So that was really then what I was going to say to you today on the inertial confinement fusion side. I'd now like to introduce you to magneto-inertial confinement fusion and some of the experiments we're doing on the NIF to investigate this. So Z-pinches were originally what were being used on these pulse power machines. Now, what happens in a Z-pinch is that you run a current through a wire, and a current carrying wire has a magnetic field that surrounds it. But when you run really, really high currents through a cylinder, for example, you also now have a J cross B force. You've got currents that are travelling in a magnetic field, just like the Lorentz force. You've got a charge going through a magnetic field, it gets deflected. You've got the J cross B force here, which acts to pinch your cylinder on axis. You have this force imploding it. Now, this was the approach that was starting to be investigated by the pulse power community. But actually, it was found that you end up generating a lot of instabilities and inefficiencies in that compression process. And so actually often the pulse power machines now, when they do Z-pinches, are using those to give you high X-ray fluences that they can use for other experiments. The MagLIF approach tries to help things by adding a laser heating stage. So you can see a schematic here for MagLIF, which is where initially we have a magnetization of a gas pipe. So your fusion fuel, rather I should say, is the gas that's in the middle. You provide axial magnetic fields, so running along that Z direction of about 30 Tesla to stop the plasmas escaping out of the gas pipe. Plasmas don't like crossing field lines, they like to go along the field lines. So by providing an axial magnetic field, you're trying to prevent the movement of that plasma out. We then have this laser heating stage of the laser passing through to already give you a bit of a plasma, give you a kickstart in getting those temperatures that you require in your gas pipe, before then applying those azimuthal magnetic fields then to pinch that plasma down and hopefully generate you megajoules of neutronions. Now, we've got the Z facility to do some of these experiments over on, and they have a laser over at Z as well. Oh, let's not do that. But the laser at Z only produces about 4 to 4.5 kilojoules of energy. We can apply axial magnetic fields on Z, so we can get 20 to 30 Tesla, and we can also do the pinch there. But if we want to go to a MagLIF fusion scheme, we need to be able to get up to these 25 kilojoules of laser heating stage, which is where the NIF comes in. So on the NIF we can get 20 to 30 kilojoules of laser heating of the gas pipes. We can also actually provide an axial magnetic field of between 0 to 30 Tesla. The only thing obviously we can't do on the NIF is doing that pinch. We don't have the pulse power, the large pulse power facility available to us. But we can still investigate the laser heating stage, which is what I've been involved in. So there are a couple of questions that we want to address. We want to have a look at the laser propagation through the gas pipe, and we also want to understand any wall material that might be mixing into our fuel. So we want to understand how the laser is going to couple into the laser entrance window. So these are gas pipes as well. You've got windows on the end to contain the gas in there. So we want to understand how much laser energy is actually going to get into the window, because we actually want all the laser, or as much of the laser as energy as possible, to go into the gas itself, not into the window. We also then want to understand how that laser propagates through the gas, and that will also depend on the density of the gas itself. And then we want to apply a magnetic field and see how that affects the transport. When we come to understanding mix, they've done some experiments over on Z to try and understand the mix, and they've added tracer elements of magnesium and cobalt onto the edges of the gas pipes, and they've tried to then locate these at later time. So on Z, a lot of the diagnostics are actually time integrated, so you don't get information about when these things are happening. But they've got spectroscopy data that show that they see magnesium and cobalt lines occurring in the middle of their gas pipe, but they just don't know when this happens. And the thing is, if you've got warm material getting into your gas pipe, this warm material radiates away energy. And so that will end up reducing your neutron yields, because you're then losing energy that actually you want to contain as much energy to drive these fusion reactions. You don't want to be losing it out there. And the earlier in time in the interaction that this loss is occurring, the more it matters. If this mix is occurring at late time, that's not so much of an issue because it won't have had as much time to radiate away energy. If it's occurring really early in time, we've got bigger problems. So we've started to do some of these experiments on the NIF because we've got time-resolved diagnostics and we've got the high-energy lasers. So there's some simulations that we've also been doing in collaboration with Sandia. So essentially we've got, if we were looking at a side-on view of the gas pipe, we've got the laser that's going to propagate through the gas pipe, and as it goes through, it actually ends up generating a blast wave. So that a blast wave gets sent out to the edge of the gas pipe and ends up bouncing back in. So this simulation over on the right-hand side is going to show you an end-on view of the gas pipe. So we're going to have our laser that would be propagating through the middle. We add tracer materials of a higher Z material over on the sides so that we can actually locate them using their line emission. But if we actually look at the simulation, you can see that the laser's propagated down, launched this blast wave out to the edge. That red line is the wall boundary. And you can see as time goes on, that wall starts to move in, as do the tracers. Before then, we don't have magnetic fields azimuthally compressing this, so it will just expand outwards at late time. But we want to check whether these simulations are actually capturing the dynamics accurately or not, so then we look to our experiments. So we've done several different experiments. We've done experiments using a warm gas pipe, which are primarily used to do the mix experiments. We've also then wrapped magnetic field coils around this to do magnetized gas pipe experiments. And then when we look to using deuterium in our targets as well in the gas to actually mimic up something more fusion relevant, because these experiments are done using neopentane gas fills because you can't put it to such a higher pressure, we then do cryogas experiments as well. But I'm just going to focus for a minute on the warm gas pipe experiments for the mix. So initially we have our laser that will come through, heat our gas pipe. You can see these are 10 millimeters long. They've got the neopentane gas fill. We actually have some tracer strips that are located out on the edges here. At later time, we actually bring through 2 further laser beams onto those tracer strips. And what we're trying to do here is that as that initial laser comes through, it's going to heat the gas pipe. You're going to launch this blast wave out, and you're going to hopefully bring off some of this tracer material. But we decided one way of trying to locate the tracer material was to bring through extra laser beams to reheat the gas and trying to get those titanium or vanadium tracer strips to emit and re-emit emission lines again that we could try and measure. So, okay, so this is looking at the laser propagation stage. So here we have what's called a gated X-ray detector. So this can take several different images at different times. So here we have 4 different times. The laser is propagating from left to right. And you can see the laser propagating down the gas pipe as we get to sort of this 11.5 nanosecond time. Depending on how much time the laser spends in the gas pipe, we can also calculate how much energy has been deposited into the target. And this is what this plot over on the right-hand side here is showing, that we have, so depending on how much time it's spent, depending on the burn through time, we can then calculate the different energies. This 15% or this 11.5% crit just corresponds to different densities that we've set the gas fill to. And we can do these experiments with different magnetic fields to see how that affects that laser propagation going through. Brad Pollock has published a paper as our collaboration that I'd point you to as well if you want to understand more about the laser propagation dynamics in these gas pipes. But we still have questions as to, are we accurately understanding how this laser absorbs and scales with density, with adding magnetic fields? There's still a lot of open questions around this. We can also then look to the mix measurements. So again, trying to understand mix, we can use these gated X-ray detectors to look at different times. But what we can also do is, on one time, these GXDs have strips that you can put 4 different pinholes images, so they'll all be at the same time, but you get 4 different images, and you can put different filters on. So we had a scandium filter, titanium filter, vanadium, and then a Kapton filter across the whole detector. And what you can see here is this is looking at our reheat stage. So this is when we have one beam coming close to titanium, one close to vanadium. And when we're looking for the emission coming from those tracer materials, we can use their transmission probability of different photon energies through the different filters. So for example, if we're looking for titanium lines, which occur at about 4.5 keV, those won't be seen through the scandium filter. Also, if we're looking for vanadium lines, which occur at about 5 keV, they won't be seen through the scandium or the titanium. They'll only have a transmission probability, well, okay, you'll get a little bit of transmission, but majority of the transmission is going to be through the vanadium filter. So I can do some simulations, because we're also going to not only get line emission, but we're also going to see Bremsstrahlung emission just from the plasma being hot. And depending how hot that plasma is, you're going to see different amounts of energy being transmitted through different filters. So this is kind of where people started to use what's called Ross pair filters. So you subtract one filter away from another. So over on the right-hand side here, I've got a plot where I've predicted what the Bremsstrahlung emission would look like through different filters. Now, if we were to take away all of the emission that came through the titanium filter from the scandium filter, then we would get the area basically contained within the green box. So this little region that would be between the yellow and the red line. And if we use the titanium and vanadium pair, we would then get the emission, actually it would be also including the green here as well, but you would basically be measuring the emission between those two filters. And if you imagine, if you had a colder plasma, you wouldn't get as much emission up at these higher energies. And so your balance of intensity between the two would change. And we can plot over on the left sort of what that would look like in terms of the different temperatures that might give you different lines, different ratios between the different filter bands. And hopefully, if it were just Bremsstrahlung emission, you would see these in your data. What happens though is that we've now got line emission on top of this as well. So this is now a plot including titanium lines. So now we can see in this green box, we're going to get way higher intensity coming through those filters. And so now when we plot it over here and try and estimate what would be going on with what temperature our plasma is at, we would now actually not be sitting on any of these temperature lines at all, because those titanium lines have started to skew things. But we can start to use this then when we're actually looking at our spatially resolved images. So when we come to looking at the titanium minus scandium filter, anywhere that we see a brighter lot of emission that we don't see coming through the vanadium and the titanium filter, that indicates we've got titanium lines there, because the green box has been enhanced, it's got enhanced emission there from those titanium lines. So for example, on these images, you can see this little white, yellow blob here, very, very close to where we expected the titanium tracer to be. That's got a lot higher emission than when we look at the vanadium minus titanium filter pair. We don't see that same enhanced emission coming through. So that indicates then that we've got titanium over there. Now, this technique has been used on several different experiments, less so using line emission, but it's something that I'd like to develop further, particularly then if we can start to try and locate these tracer propagations into the gas pipe over time, and then help inform those simulations to work out if the simulations are getting the dynamics correct or not. Okay, so that was a bit of a summary then of some of the different projects that I'm involved in. There are more on top of this, but yeah, hopefully that was enough of an overview to give you a bit of flavour of some of the things I'm involved in. Yeah, hopefully I've been able to show there's lots of large-scale facilities out there that we can investigate a variety of different experiments. There's often times it's actually really useful to have experiments and diagnostic development going on at the same time, that you can try and optimise your diagnostics as much as possible to get the best results from your experiments. And for me, I am very much fascinated by the magnetized environments. There's a lot of physics occurring there that maybe hasn't been explored as much, and I think it's really exciting. So yeah, I look forward to collaborating with some of you. Well, thank you.
Questions?
For the image plate proton radiography stacks, so I know you get the structure back. Do you have an absolute, because proton radiography has like a 1-to-1, like 100% proton detection efficiency. Have you figured out an absolute calibration for understanding the proton fluences from image plates?
No, and that is also something that we need to do. So at the moment, what I've been using is, I had the graph at the bottom of the slide there from Bonnet et al. You can, let's go back to it. Okay. Anyway, there is a plot which other experiments have calibrated up their image plates so that when you have a proton hitting the image plate, you can work out from knowing, you have to know the energy of the proton that hit it, but then you can work out the photostimulated luminescence, the amount of energy deposited per proton on the imaging plate. But this is something that I think needs to be further calibrated to fully understand. Yeah.
Any other question? Very good.
What diagnostic, so you're using proton radiography for magnetic fields, is that the main diagnostic for probing magnetic fields, or are there other diagnostics you think would be useful?
So you can also use Faraday rotation to image magnetic fields, but the issue with Faraday rotation imaging, for those of you that aren't aware, when a laser travels through a magnetic field, you get a change in the polarization of the beam. So you need a very well polarized laser beam going through. When you see a rotation in that polarization of the laser, you can infer then from that the density and the magnetic field strengths. But depending on the strength of your magnetic field, you might not see much of a polarization change. And it can be a more challenging measurement to extract out for some of the laser experiments, but it could be something that there are certain experiments that it could be applicable to. Yeah.
Are your plasmids below the critical density of transmission?
So this is one of the issues for when we're face-on probing. You've got to go through solid target material. When you go side-on, you could get information like that, but then the magnetic fields are toroidal, so they're not always going to be. You need your magnetic fields to be in certain directions located relevant to the polarization. So yeah, it wouldn't necessarily be the best. Maybe along sort of a gas pipe, you would be able to use something like Faraday rotation. But yeah, it's something that I haven't explored because of the critical densities for my plasmas in general.
Thank you.
Is the view that the magnetic field fluctuations are affecting the capsule implosion in this type of experiment?
Yeah, so the thought with the magnetic fields that might be formed in a Hohlraum, for example, is that if you then have magnetic fields which are affecting where the density and where the plasma is propagating out to, say we've now got actually much stronger density gradients out at the edge of the plasma bubble, because the magnetic fields are then preventing the plasma from expanding out, you've then got your laser, which is no longer going to be depositing as much energy at the gold wall, but is also now seeing this other density gradient and depositing energy out there. So it's not necessarily, okay, there might also be some other effects of the magnetic fields affecting polarizations, which might have other effects if we get strong enough magnetic fields in a Hohlraum. Cross-beam energy transfer being one of them that's affected by magnetic fields. But yeah, you will get density gradients that then lasers get absorbed there rather than at other sources. And at the moment with Hohlraums, it's turning out that very, very small changes are actually making pretty large differences now. So it is chasing some of these smaller adjustments that we might be able to make that actually could help push the yields even higher.
In one of the proton detecting plate pictures earlier on, after a few nanoseconds, it was showing like a pentagon shape in the etching. And is that something that comes from the geometry of the lasers coming out of the Hohlraum, or is it something else?
So that we're still trying to work out. I think I know the images you were talking about. It's some of these features here.
Yeah.
So here they would have had lasers coming in, but these are almost like plasma bubbles that are coming off the walls here. But some of these structures they're actually thinking might be coming from the windows as the laser's propagating through as well. So yeah, you'll get plasma expanding off the walls. The laser walls are all sort of projecting around, and there will be a dependence. You will see fields coming from those plasma bubbles expanding off the walls, but there might also be effects for some of these structures from the window materials as well. So we're trying to isolate in an experiment next year what's coming from wall, what's coming from windows, what's coming from having a gas in there. Yeah, there's lots of different physics going on, and we don't understand it all.
Thank you. Before we close, if you took a chair from another room, please bring it back. And I want to remind everyone that right after this we have our back to school event on the 4th floor. There is food and games, and please join us. Everybody's welcome. And let's thank again Ellie.